Swayam Prabha. Digital India. Educated India.
So today we are going to learn analysis of variance. In short form, it is known as Anova. Now there are situations when we are interested to examine differences among the means or more than two groups. So we have already studied how to find out the difference between two means, whether the means are significantly different from each other or not. So when there are only two means involved, then we do generally Z test, or we can do T tests, which you have already learned. But we may sometimes face situations when we need to compare between multiple means, just not two. It could be 3, 4, 5 or more than that. This kind of situation arises in those cases when you say two groups. The groups may be classified according to the levels of a factor of interest. Now, how? We'll see that here are few examples. Like, say, parachute fabric manufacturers may be classified into several groups defined by simply supplier 1, supplier 2, supplier 3 and supplier 4. So just like vendor 1, vendor 2, vendor 3, vendor 4. Similarly, operators can be classified as operator 1, operator 2 and operator 3. We are not restricting to 3, it could be 4, 5, 6 also. Machines of different makes can be also grouped as machine 1, machine 2, machine 3, machine 4. So, and then we want to really test whether there is a differences in the performance of the machines in terms of the quality of the material that machine is going to produce. Whether uniformity, let us say an example, yarn uniformity. And let us say we have machine manufacturers from three different machine manufacturers are there, and we want to test that which manufacturer's machine, or we have existing machines and we bought some new machines. We want to compare whether the mean uniformity in the yarn produced by 3, 4 different machines that we have, are they different from each other or not? So this is a typical example. Similarly, we can try to judge the performance of operator 1, operator 2 and operator 3. So we can judge it based on their some performance criteria and see whether the mean performance criteria of operator 1, operator 2, operator 3 are they different from each other or not. So such kind of situation may arise and we need to find out. So first of all, let us discuss that variations in results, that when we conduct some experiments, there are some variations which will be there in the results. Let us say we want to study the effect of some treatment or some factor on a response variable. Response variable could be the strength of yarn, uniformity of yarn, fall level in yarn or fall level in fabrics, or elongation of the yarn or fabric, whatever it is. So we want to, these are my response variable, and we want to see the effect of some treatment of some factors. We might have changed some process parameters at 3-4 different levels we might have used, and we want to check now whether the uniformities that you are getting or for level that you are getting in the yarns, whether they have really, whether they're really differing from each other or not. The results of any variation that we see, that can be, we can have different sources of variations. Now, what are the different causes of variations? The sources of variations could be, one, due to main factors or due to subsidiary factors. And the subsidiary factors which can affect the variability in the results, there are two types. One is controllable factors and other is uncontrollable factors. So one is, therefore, variation is due to change in some main factors, and the other one is subsidiary factors, where it can be again classified into two groups, controllable and uncontrollable. We'll see with an example. Let us say effect of shrink resistant treatment on the area shrinkage of knitted fabrics, or any, for that matter, any fabric, knitted or woven. So factors affecting the results, if we classify them, first one is type of shrink resistant treatment. What kind of treatment was given to the fabric? So shrink resistant treatment, whatever treatment or whatever chemicals had been used, that is one which is going to, and what was the amount of those chemicals, that can affect the results. The second variation that may come is because of the type of fabric, and the third one is the type of washing machine, because when you want to test the shrinkage, you have to actually place the fabrics within a washing machine, and then we wash it for a certain amount of time, and then we remove the fabric and check the dimensions of the fabric after washing and what it was before washing. That is how we check the shrinkage behavior of fabrics. So type of washing machine can affect the results. Length of wash, the duration of the wash can also affect the results, and the temperature of water that has been used during washing, that can also affect the result. So these are different types of factors which can affect results. The other one is specimens of the fabric actually tested. Which particular specimen of the fabric was tested? If I have a roll of fabric, then exactly which specimen, which part of the fabric was chosen for performing shrink resistant treatment, and then actually once the treatment has been given, then are we biased in choosing the specimens from the treated fabrics? That can also affect the results. So specimen of the fabric actually tested can also affect the results. And which run of the machine was used, that can also affect the results. First run or second run or third run, maybe as we go from one run to another run, there may be some changes in the behavior of the machine, and therefore it can also affect the results, or the variability gets introduced into the results. The other one is errors in measuring the fabric dimensions. So whether the scale that has been used, whether it is correct or not. The other one is knitted fabrics are very stretchable fabrics. they are not very stable. So while measuring the dimensions of the fabric, digital fabrics, how much stretch is getting introduced while I am measuring the dimension, this can also affect the results. So errors in measuring the fabric dimensions, that can also have an influence on the result. So we can see there are so many uh, factors which can affect the results. Our aim was to study the effect of shrink resistant treatment. So that we call main factor. That is the main factor which is supposed to affect the results. The factors, rest of the factors 2, 3, 4, 5 are known as controllable factors because these factors is within our control. We can make sure that while performing the experiments, we keep them constant. We don't change them. Like length of wash, we can fix the length of wash. It will not vary from fabric to fabric, or fabric specimen to fabric specimen. We can keep it fixed at 10 minutes or 20 minutes, whatever it is. The temperature of wash also can be fixed at a certain temperature. Type of washing machine also we can fix. If we have 4 or 5 different washing machines, we will only choose one machine and do all the tests in that machine only. The last 6, 7, 8, these are the factors which are uncontrollable. That is, we do not have control on them. So the factors that can affect the results are the main factors. That is what we want to actually study, the effect of those factors. Some of the factors are controllable factors, so we'll try to maintain them at a constant level. We'll make sure that they don't change. The other few factors are uncontrollable factors. These factors are not within our control. Specimen of the fabric is actually tested. See, once we cut a specimen, that specimen goes for testing. The next one that I cut, that is different from the previous one. That could be different from the previous one. So therefore, specimen to specimen variation which could be there in a fabric, that is something is beyond our control. Then which run of the machine used? This is also difficult to control because if we choose some specimens in the first run, in the second run there will be some more specimens, third run there will be some more specimens. So there is a chance that run to run differences, if at all, exist in the performance of the machine in terms of its washing performance, then that can also affect my results. This is something which is difficult to control, or we have to think that whether we have a means to control it or not. And errors in measuring the fabric dimensions. Here there is a chance of error, as we said, we have discussed earlier. Point is that it all depends upon the skill of the person who is measuring the fabric dimensions. So that one has to make sure that whatever specimens we are going to test, the dimensions are measured and there is no undue stretch that we give to the fabrics. So that sort of subjectivity which is possible in measuring the dimensions could be there, which is also uncontrollable. So all these are the reasons for affecting the results. Now we are going to discuss this particular topic with an example. Here, what you see in this table, times for water to penetrate 4 makers of showerproof fabric. See, this is what is given here. And what we see here is these are the 4 different manufacturers, 1, 2, 3, 4, and these are the data. This data is actual time to penetrate minus 100. 100 is a common factor which we have subtracted from the actual time for all the readings. Why we have done it? This is what we have done in order to make sure, or in order to ensure, we should say, that the disease that we get, they become 1 or 2 digits, so as to help me in the calculation part. If I don't subtract 100, all these figures that you see, some of those figures will be coming in, they will be 3-digit figures, or some of them 2-digit figures. There will be no single-digit figure. So to help in the calculations, we can subtract a constant figure, and by doing so, the results are not going to be affected. And then, if this is what is there, we find out the means. So to find out the means, we have to first find out what is the total value. These are 4 different manufacturers, and we find out the respective means 5, 30, 39 and 18. So now the question is, are the sample treatment means different from each other? What we see the mean? One mean is 5, the another mean is 30, another mean is 39, another mean is 18. The question that we are raising, are the sample treatment means different from each other or not? Apparently, from the, if you look at this figure, it appears yes, these two are very high value and these two are less value. But we have to actually go for statistical analysis. Based on that, we have to make our conclusions. So it is not based on any subjectiveness, should not be there. There has to be a statistical backing in whatever conclusion we are going to draw. So here, these are the 4 different means that we have, and we have to compare whether the means are differing from each other or not. So therefore, our hypothesis will be that null hypothesis will be treatment means are all same, and the alternative hypothesis would be the means are not same or they're differing from each other. So the 2 hypotheses will be this. So this will be our H0 and this will be our H1. The variation in the treatment responses is used to decide whether or not the treatment effects are significant or not. The data is treated as random samples from a normal populations having same variances and differing, if at all, in their means. So what we treat first, that there are random samples and coming from normal population having same variances also. So we are basically saying that they are coming from a normal distribution populations having same variance or same standard deviations, and the samples has been chosen randomly. So there is no bias in choosing the samples. So the only difference is that they may differ only in terms of their means. Now let us make a visual presentations of the data. Here the same data make of the fabric 1, 2, 3, 4. So here on the right hand side, you see the visual presentation of the data. Now what is here on the x-axis? The x bar, that is whatever is the grand mean that we have seen. If you look back the previous table, the grand mean was there, So the grand means, this is the line indicating the grand means. This is the zero value. This side, the y-axis is penetration time in excess of 100 seconds. So what was the value? Minus 100. Those values are here. So here it is 0, this side is negative, and this side is positive, this side is negative. And these are the 4 different make of fabric. These dots that you see, the dots are basically the data points. So what we see here, this is the 0 line, and if we plot the data, this will look like this. The data points will look like this. This is for these 5, these all are for fabric manufacture 1. These 5 are for fabric manufacturer 2, and this is for fabric manufacturer 3 or 4. This is the 3 and this is 4. This point should have been somewhere here, probably it has shifted, so you can ignore that, doesn't matter. Now any data can be considered to consist of 3 parts. Any data. We will focus on the very first data point of the 3rd fabric manufacturer. And this data point that we have chosen is X31. So 3 stands for the 3rd manufacturer and the first data point, so that's what represented as 1. So X31 is also shown by this, by this point, which is X31. You see the colors are exactly same, so it is representing this value of this. So X31, from if you see X31 is represented or you can say that the distance of X31 from this 0, 0, 0 line is represented by this DA. If I draw a line, A point is here and D is here. So from D to A, this is what is representing X31. And this DA, we can see it has 3 parts. We can split DA into CD plus BC plus AB. So CD plus BC plus AB. You just see here, CD is from, this is what is CD, from where to there. So from the 0 line to where our grand mean is existing, that line. This is what is CD or DC, whatever we say. Then from here to there, that is from the grand mean to the point B. What B represents? Now the B represents these lines. These represent the X3 bar. That is this is the average. This point, these lines are the average of the readings that we get from the fabric manufacturer 3, or the 3rd fabric manufacturer. The mean is here. So BC represents the difference between the grand mean and the mean value of the make of the fabric 3. And then we have another component AB. AB is called as random error. So from mean to the difference between the mean value, local mean value, and a particular value that we have obtained while performing the test. This difference, which is represented by AB, is representing an error which is E31. So therefore X31 can be written as the sum of CD plus BC plus AB. So CD is how much? CD is basically x bar. From here to there, the distance is how much? X bar minus 0, so it is x bar. Then BC is how much? BC is x3 bar minus x bar. And E3, that is AB, you can say, is x31 minus x bar 3. So we can write, therefore, x31 as x bar, grand mean, plus T3 plus E31. So T3 is, we call it treatment effect, and E31 we call it the error, the random error. See, from the mean, so we have got one value here, another value here, another value here, another value here. 1, 2, 3, 4. There are 5 readings. So these readings are around the mean of fabrics that was procured from the manufacturer, third manufacturer. So it is x bar plus T3 plus E31. So what is x bar? 23. In this case, what is T3? Difference between these two, and therefore it will be 16, and the difference is shown here. So we can write x31 is 23 plus 16 plus 10. So the value of x31, if you look back the original table, you will find whatever value was there, that value can be written as summation of these three, 23 plus 16 plus 10. So this will be true for all the manufacturers of the fabrics and for any reading. So for x3, suppose this is x34, we can also find out from this, for this particular point, what are the corresponding values. So one can therefore write, now we can go for a generalized presentation of data. Now what we write, that on the first row we write these are as treatments or factors. Even though this is the manufacturer, so manufacturer 1, manufacturer 2, and 3, we can write them as treatment. As if I am doing an experiment, and these are the different treatments. So treatments, so we write 1, 2, 3, 4, 5, I, it can go up to, there are C number of treatments are there. And then under each treatment, we have the corresponding data points written as x11, x12, x13, x1j, x1n. There are n observations are there. These observations are for treatment 1. For treatment 2, we start with x2, x21, x22, x23, x2j, x2n. For third, we start with x31, x32, x3j, x3n. So like we have C different treatments. C could be 3, 4, 5, 6, 7, and there are n different observations under each treatment. N could be 5, 6, 7, 8, 9, 10, whatever number of readings we want to take. So any value xij has 3 components. One is the grand mean, plus this is called treatment effect, and this is called the error. We write it as mu. Treatment effect is difference between these two, mu I minus mu, and xij minus mu y is the error part of it. Therefore, grand mean, effect of ith treatment, and the random error. These are the 3 different components. Now, the hypothesis is, if it is a generalized table, so we have C different treatments, and if we say whether the means are different from each other or not, treatment means. So we write, null hypothesis will say the treatment means are same. So therefore, mu1 will be equal to mu2, will be mu3, it will be equal to mu c. The c number of treatments are there. Or we can write null hypothesis as tau1 will be equal to tau2, will be equal to tau3, tau c. These are representing the effects. All these effects are same. Both of them meaning same thing. The alternative hypothesis will look like at least two of the treatment means are unequal. Any two. The null hypothesis says all the means are same. Alternative hypothesis we will write that any two means are different from each other. Any two, maybe mu2, mu3, or mu3, mu5, whatever. That will be my alternative hypothesis in this case. If we write it mathematically, we write mu y is not equal to mu y plus 1. To test this, some assumptions about the error term is to be made. And assumptions are what? One is EIJs, that is the errors, are independent random variable. This is one assumption we have to make. And they are normally distributed with a mean 0 and variance sigma square. The variance is sigma square. So the error terms have a mean value which is 0, but variance sigma square. These are the assumptions we need to make for analysis of variance. Now when you go for test of significance, in Anova, the total variation is subdivided into two parts. One, differences between groups or between treatments, and variation within a group or within a treatment. Variation within treatment and variation between treatments. If we assume that null hypothesis to be true, then the variance can be estimated in two independent ways. Two independent ways we can find out the variance. One, by considering the data within the treatments, by considering data within treatments. So within treatment data we will consider, or from between treatment means. Sigma square can be estimated by two different ways. We will see how we are going. What do these two statement means now? The test we perform thereafter is, once we have that, if we can find out, that is estimate the variances by considering the data within treatments and also from the treatment means, then we need to perform a test that whether the variances are of same size or not, and for that what we perform is F-test. So we are actually trying to find out the variances, and we have already learned earlier that if we want to check whether the variances are different from each other or not, then what we do, we take the ratio of the variances and that follows F distributions. So that corresponding test is known as F-test. So here also basically we will be performing F-test on what? On the estimated variance. We again go back to the table which you have seen it earlier. The same table we are writing it here. Now here you see that how we are calculating first estimate of variance. We said there are two ways to estimate the variance. One is variation within treatments. So within treatments, this is treatment 1 and these are the values. So what is the variation between these values? x11, x12, x1j, up to x1n. Similarly, we go for treatment 2, again find out what are these are the values, then what is the variation between them. And these variations are calculated and they are written here. So variance of treatment 1 is S1 square, treatment 2 is S2 square, S3 square, Si square, A square C. There are C number of treatments are there. So these are the variances. And variance calculated is variance is square of standard deviations. So we are basically trying to find out the square of standard deviations. That is what is variance. And variance standard deviation calculation you have learned already how to calculate the standard deviations. Same formula we will apply here, but we will take this, we will not make under root, we take the square. That is what variance is. So this is the formula for variance. And for each of them, for each statement, we will find out the corresponding variance and they are tabulated here as if S1 square, S2 square, S3 square, like that. So different estimate of sigma square therefore becomes, they are all basically estimate of sigma square. This is one estimate, this is another estimate, this is another estimate, this is another estimate. So all of them are basically estimate of what? Sigma square. And therefore the better estimate is that we combine them together and find out the average variance. So the average variance can be worked out. All those variances are added and divided by C. C are the number of variances we have. So this is what will be the average variance. And we write it as A square W, because the calculation method is that we first find out the variations within for each treatment and then club them together, and then thereafter we find out what is the average value and we call it A square W, variance within. These are the simple steps to find out the variance, which is an estimate of population or variance of the error term. The second estimate of variance is variance between treatments. For that, what we do, if H0 is true, the data can be regarded as constituting C samples from same populations, as if they are C samples I am choosing from the same populations. The sample size is N, population variance is sigma square, and the sample means are shown here: x1 bar, x2 bar, x3 bar, xi bar, x bar c. These are the individual mean of treatment 1, treatment 2, treatment 3. So these are as if means, sample means. So if these are the sample means, then an estimate of variance will be what? Sigma xi minus x bar whole square by c minus 1. That is the formula. Here these are my values and we have to find out what is the standard deviations between these means, between all these standard deviations, where x bar is indicating the grand mean This is what is x bar. So xi bar minus x bar whole square by c minus 1. Sum them up, we get an estimate. We write it s dash b square. Now that's an estimate, and we already know that the variance of sampling a sample means sigma square x is sigma square x bar is sigma square by n. Population variance by n, or sigma x equal to sigma by root n. That is what variance of sample mean. And hence, this is estimated by this value. So we write that s squared b, where there is a hat here, is sigma squared by n. And therefore, a good estimate of sigma square is n into s dash squared b. That is the estimate of sigma square, and we write that as s squared b. So x squared b is n into s dash squared b, where s dash squared b is this, what is written here. So these are the two different estimates of sigma square. So if H0 is true, these two estimates, S square W and S square B, are both of them are estimate of sigma square. Therefore, the ratio will follow F distribution, because it is the ratio of variance with C minus 1 and C into n minus 1 degrees of freedom. This is the degrees of freedom while calculating S squared B, and this is the degree of freedom while calculating S squared W. So if H0 is not true, S squared W will still be an estimate of sigma square, but S squared B will be inflated by the differences between the treatments. If H0 is not true, that basically means that the treatment means are differing from each other, and therefore the value of S squared B will be quite high in that case. It has been shown that the average value of S squared B is this equation. We are not going to really, you need not to know the derivation of these equations, but what it shows that A squared B is summation of sigma square plus n by c1 root n by c minus 1 sigma tau y whole square. What is the importance of these equations? It basically means that the average value of A squared B is always greater than sigma squared, because A squared B has one term sigma squared plus an additional term, this one. So A squared B will be always greater than sigma squared, provided TI's are 0. Unless all TI's are 0. If tau y is at 0, in that case, this term is going to be equal to 0, and therefore A squared B will be equal to sigma squared. So if there is a treatment effect, A squared B will be always more than sigma square. Hence, calculated F value based on this ratio will be significantly large if H0 is not true. So when we have to reject H0, that basically means in that case the calculated value of F that will be very, very large. And the test for the differences between more than two treatments has become a comparison of two variances finally. So that is the beauty of this analysis of variance, that when you want to compare multiple means because of some different experiments or different treatments, then the comparison can be done easily by comparing the variances calculated in two different ways. One, by considering the means between the treatments, and the other considering the values that we get within treatments. So these are the two different ways that we can find out the variance. We call them variance between treatments and variance within. And after that, we have to take the ratio to find out what is the F value, and that F value we have to then compare with the table F value for a given level of significance. And if it goes beyond that, based on whether it is less than the table value or less than or greater than, accordingly we'll say whether the null hypothesis is true or not. So these are the theoretical background of the analysis of variance. These analysis of variance table now we are going to discuss. This is a typical way we represent our results. So here is a table. This is the typical format. First column, sources of variation. Second column, sum of squares. Third column is degrees of freedom. Fourth column is mean square, and fifth column is value of F. And what it is written here, you can see between treatments, this value, this formula is well known to all of you. When I divide what is there in column 2 by column 3, what we get is variance. Or basically it is a standard deviation calculations. If I take the under root of this divided by C11 and take under root, this becomes SB instead of S squared. So what we are writing here is the formula for calculating the variance. This divided by this is the variance. We call this between treatment variance, because here you see, here is the grand mean and the individual treatment means. This difference is squared, they are added, and then they divided by degrees of freedom, and we find out what is your mean squared. Similarly, within treatments, this is the formula. When I divide 2 by 3, we get S squared W. That is what is within treatment variance. And if I add to this and this, we get this figure. This is called the total variation which are there. That is each individual values minus the grand mean, and you take the differences, square them up and sum them, that is entire data set is involved in this particular calculations, and that divided by c minus 1, that become my, in this case, degrees of freedom. That gives total variations. So this is one estimate, this is another estimate, and we take the ratio of these two and find out to what is the calculated value of f. Last row in the table shows the sum of squares and degrees of freedom will be calculated if the variance of all chain observations are found ignoring the classifications. So this is how the data or the Anova table is represented. Now, to simplify the calculation, what we do, just to save some time, but today because of the computers are there and softwares are there, these may not be required at all. But if you want to do the calculation manually using a calculator, then these are the, just to simplify the calculation procedure, what we do, we first find out the value S1, which is sum of squares of all individual observations. This is what is xij squared, sum over I and j, I varying from 1 to c, j varying from 1 to n. Then S2 is this ratio, and which is sigma ti squared by n. And S3 is t squared by nc. So we find out S1, S2 and S3. So this is relatively simple to calculate when we have a calculator in hand. And in that case, the sum of square can be written as S2 minus S3, and this sum of square within t domains can be written as S1 minus S2. The total is sum of these two. So if I add this plus this, you see S2 and S2 will cancel, and we will left with S1 minus S3. So always the last row is the sum of the previous two rows. And these are the degrees of freedom. Here also, if I add this with this, we'll get this figure. These are the mean square value we need to calculate. So by S1, S2, S3, if I do it, my calculation time may reduce. But as I said, if you have a software and a computer with you, you need not to do this. You just feed the data, the computer will generate this table. Now the data with which we started, that is water penetration time. And with that example, now we are performing this Anova test. So the values are stated here, all the numerical values. These are the corresponding mean value. This is the grand total, and these are the grand mean. 23 is the grand mean. So we find out what is S1, what is S2, what is S3. And based on this formula, we just calculate them. These are the figures we get. S1, S2, S3, C equal to 4 in this case, and N equal to 5. N is 5. You just count 1, 2, 3, 4, 5. And C is 4. We have 1, 2, 3, 4. 4 manufacturers, so therefore C is 4. And we have 5 readings for each manufacturer, so N is 5. With this table with the numerical data will look like this. Sum of squares will actually work out to be 3270. So within treatment, sum of square is going to be 2606, and the total is sum of these two. So whether I do this way or I just add these two, it should give me the same result. These are the degrees of freedom in this case. These are the mean square. Divide 3270 by 3, 2606 by 16. These are the values you are likely to get. And therefore the F value will be 1090 divided by 162.9. This will give a figure 6.69. So in the present case, the calculated value of F is 6.69. Now the table value of F for degrees of freedom 3 and 15 at the level of significance 0.01. This figure in the table will find 5.4. So for this you need to consult the table, F table, and find out what is the value of F. That is 5.4. So observed value in this case, or calculated value, whatever we say, is greater than the table value, since 6.69 is more than 5.4. So what should be my conclusion? So calculated value is more than the table value. So it has gone too far. So the conclusion will be the significance less in this case is less than 0.011%. We therefore reject the null hypothesis and conclude that there are real differences in the make of the showerproof fabrics, because the F value is much higher. This calculated value is much higher than the table value at those level of significance. At level of significance 0.01 or 1%. So null hypothesis will be rejected, and we will say that there is a real differences in the mean wetting time or penetration time of water through the fabrics. Only this is what we can conclude. But which one, how, if we want to compare between any two, then we have to go for t-test. This is only going to give you the answer to the questions whether the means of these four different manufacturers are different from each other or not. And the answer to that is yes, there is a difference between them. So they are not same. Another example. The following are the number of mistakes in 5 successive days by 4 technicians. So the mistakes of 4 technicians are given. Test at the level of 0.01 significance whether the differences are due to chances or not. So we have 1, 2, 3, 4 technicians, and these are the number of mistakes they have committed. So procedure is exactly same. To see here, we have number of mistakes minus 10 we are doing. What is the advantage? I see many figures which are has become only 1 digit, and few figures have become 0 also. So this is going to tremendously help me in doing the calculations manually. So we'll be able to save a lot of time, and the possibilities of committing an error in during while calculating also will be much less. That's why this is what we have done, number of mistakes minus 10, and these are the figures. Some figures have become negative, some have become 0. That is fine. So you find out the total under each column, and then find out what is the value of S1 square. Or S1 square will be, you square each of these then. So you have to have another table where you put the square values. or you can write the square values on the side of it. So these are the squared values of technician A. This is for technician B. This is for technician C. This is for technician D. And if we add them all, we get a figure 123. S2, the formula is there, sigma Ti squared by N. So we have to find out the Ti squared. So each total we have to square it. So first total is -1. If we square it, it becomes +1. Second one is 9. Square it, it becomes 81. Third one becomes 25. The fourth one becomes 0. We add them together, divided by 5. This will give you a figure 21.4. Next is S3, T square by NC. T square we have to find out some square of grand total. So grand total, whatever is the grand total, we have to find out the square of that. So grand total we have to add this plus this plus this plus this. If I add them, grand total, how much it will be? -1 plus 9 plus 5 plus 0. So 9 plus 5, 14, minus 1, 13. So square of 13, it becomes 169. And NC is 5 into 4, 20. So this value becomes 8.45. So once we have these values, then we use this table and we write down the formula. S2 minus S3, this is the value. S1 minus S2, this is the value. S1 minus S3, this is the value. These are the degrees of freedom. This is my A squared B, this is A squared W. Thus divide 12.5 by 3. 101.6 divided by 16. So, and if I do this, I get a figure 0.678. That is my calculated value of F. And now we need to know what is the table value of F. So table value of F in this case is going to be at the level of significance 0.01. If it is stated, it is fine. If it is not stated, then you assume a significance level 0.01 or 0.05, then you are free to choose. So that is 5.29. So calculated value is much less than this. So we'll conclude that the differences are not significant in this case. Therefore, H0 is going to be true. So there is not significant differences between the means. That is the mean mistakes committed by the 4 different technicians. We have one more examples. Consider an experiment with 4 groups with 8 values in each. The Anova summary table is shown below. Fill the missing results. And second is at test at 0.05 level of significance whether all 4 groups have equal population means or not. So there are 2 questions which are there. First, we have to fill the missing results. So you see here is a table and some data is given. Rest of the data are not given. What is given here? 2 things. 4 groups. C is 4 and other data given is N. N is 8. These 2 are also given, but what is there here? Here you see these things are not stated. We have to find out the missing values in this table. How to solve? C and N are given. So we put the values of C and N in the column number 2 to find out what is degrees of freedom. We get this figure. Next, we can now find out, if I know this and I know this, I can find out what is this value. Because this, whatever is here, this divided by 3 will give you 80. So that means this figure SSB, in this case, between treatments variance, 80 into 3, it will be 240. So we get the figure 240 here. And this was already stated. We have found out the value of C here. So A squared W is going to be this divided by 560 divided by 28, it is going to be 20. So this gets filled up, this also gets filled up. So if I know 80 and 20, I can find out what is the calculated value of F, which is 80 by 20, that is equal to 4. And C n minus 1, we can easily find out because C and N anyway was given right in the beginning. We could have found out earlier also. So this is 31. So I have all the missing points. The table is all the missing points we have been able to find out that they are already there. Now the second point was whether there is a difference exist or not. So what we have done, this is the calculated value. And what is the table value of F? Degrees of freedom of 3 and 28. So 3, 28 and level of significance 0.05. In this case, if we choose, we get a figure 2.95. So who is more and who is less? The calculated value is more than the table value. And therefore, we reject the hypothesis, null hypothesis. We will say, yes, there is a difference. F value is much higher than the expected value of F at the level of significance 0.05. So that is how conclusion would be. And if few values are given, if you are not given, you apply your logic to find out how to find out the missing values. This is just one example. With that, I think we come to the conclusion of this particular topic, that is ANOVA, and this is known as one-way ANOVA. That is, only we have either a set of treatments or a group of machines, a group of operators. So this is just one-way ANOVA. We'll also learn about the other ANOVA, which is two-way ANOVAs. Both of them are, they are very frequently, they may be coming during your, while you are working in organizations. So the ANOVA is all about trying to find out whether the means are differing from each other or not. So the means mean just not two mean, it has to be more than two means. And to find out that whether difference exists between them or not, we are doing it through F tests. That is how we perform this analysis. And if we want to compare between any two, then we have to perform t-test or z-test as the case may be. With this, we close today's lecture. Thanks.